Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase synchronous motors. By solving these problems, we shall learn how to compute the amount of electrical power that gets converted into mechanical power. If a three-phase synchronous motor is excited, its input power Pin equals to 3 times Et into Ia cos phi, where Et is the terminal voltage per phase, Ia is the armature current per phase, and cos phi is the operating power factor. For star-connected armature winding, Pin equals to root 3 times VL into Ia cos phi, where VL is the line-to-line terminal voltage. Let us draw the per-phase equivalent circuit of a three-phase synchronous motor. We can write induced EMF per phase E0 equals to Et minus Ia into Zs, where Ia is the armature current per phase and Zs is the synchronous impedance per phase. From this expression, we can write armature current Ia equals to Et minus E0 divided by Zs. If we subtract armature copper loss from input power, we get the expression for mechanical power developed. Pm equals to Pin minus P copper, where Pin is the input power and P copper is the armature copper loss. P copper equals to 3 times Ia square into Ra, where Ia is the armature current per phase and Ra is the armature resistance per phase. If Ra is neglected, input power Pin is approximately equal to 3 times E0 Et by Xs sine of delta, where delta is the torque angle, which is also known as power angle or load angle. A 20-pole 6.6 kilovolts 50 Hz three-phase star-connected synchronous motor has synchronous reactance per phase 2.5 ohm. The generated voltage per phase is equal to 3600 volts. At full load, rotor poles are displaced by a mechanical angle of 3 degrees from its no-load position. We have to calculate the total mechanical power developed. Let us first write down the given data. Number of poles of the machine P equals to 20. Line-to-line terminal voltage VL equals to 6.6 kilovolts, that is equal to 6600 volts. Since the armature winding is star connected, terminal voltage per phase Et equals to VL by root 3, that is equal to 6600 divided by root 3, that gives us 3810.5 volts. Given generated voltage per phase E0 equals to 3600 volts and angle of retardation delta equals to 3 degree mechanical. Since theta electrical equals to P by 2 into theta mechanical, we get delta equals to 20 upon 2 into 3, that gives us 30 degree electrical. Synchronous reactance per phase Xs equals to 2.5 ohm. Since the armature resistance is negligible, the expression for mechanical power developed Pm equals to 3 times E0 Et by Xs into sine of delta. Using values we get 3 into 3600 into 3810.5 divided by 2.5 into sine of 30 degree. that gives us 8230.7 into 10 to the power 3 watts or 8230.7 kilowatts. A 200 kilowatts, 440 volts, 50 hertz, three-phase star-connected synchronous motor operating at 0.866 leading power factor has full load efficiency of 90%. The armature resistance per phase is 0.2 ohm. We have to determine total mechanical power developed. Let us first write down the given data. Shaft power PO equals to 200 kilowatts. Efficiency of the motor eta equals to 90%, that is equal to 0.9. Line to line terminal voltage VL equals to 440 volts. Operating power factor cos phi equals to 0.866 leading. Armature resistance per phase RA equals to 0.2 ohm. Let us now determine input power. Pin equals to PO divided by eta. Using values we get 200 divided by 0.9, that gives us 222.2222 kilowatts or 222.2222 into 10 to the power 3 watts. Since input power Pin equals to root 3 times VL into Ia cos phi, we get expression for armature current. Ia equals to Pin divided by root 3 times VL into cos phi. Using values we get 222.2222 into 10 to the power 3 divided by root 3 into 440 into 0.866, that gives us 336.71 ampere. Now we shall determine copper loss. P copper equals to 3 times Ia square into Ra. Using values we get 3 into 336.71 square into 0.2, that gives us 68.0242 into 10 to the power 3 watts or 68.0242 kilowatts. Mechanical power developed. PM equals to Pin minus P copper. Using values we get 222.2222 minus 68.0242, that gives us 154.198 kilowatts. The resistance and synchronous reactance per phase of a 4-pole 3-phase star-connected 80 kilowatt 400 volt 50 hertz synchronous motor are 0.05 ohm and 0.5 ohm respectively. Assuming an efficiency of 90%, we have to calculate open circuit EMF per phase and gross mechanical power developed for full load 0.8 power factor leading. Let us first write down the given data. Line to line terminal voltage VL equals to 400 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.9401 volts. Given armature resistance per phase Ra equals to 0.05 ohm and synchronous reactance per phase Xs equals to 0.5 ohm. Operating power factor cos phi equals to 0.8 leading. Given shaft power P PO equals to 80 kilowatts. Efficiency of the motor, eta equals to 90%, that is equal to 0.9. Let us first calculate input power. Pin equals to PO divided by eta. Using values we get 80 divided by 0.9, that gives us 88.8889 kilowatts, or 88.8889 into 10 to the power 3 watts. Expression for input power, Pin equals to √3 times VL into Ia cos phi. Therefore, expression for armature current, Ia equals to Pin divided by √3 times VL into cos phi. Using values we get 88.8889 into 10 to the power 3 divided by √3 into 400 into 0.8, that gives us 160.375 ampere. Let us now calculate copper loss. P copper equals to 3 times Ia square into Ra. Using values we get 3 into 160.375 square into 0.05, that gives us 3858 watts, or 3.858 kilowatts. Now we shall determine gross mechanical power developed. PM equals to Pin minus P copper. Using values we get 88.8889 minus 3.858, that gives us 85.0309 kilowatts. Now we shall write down synchronous impedance per phase in phasor form. Zs equals to Ra plus Jxs, that is equal to 0.05 plus J 0.5 ohm. This may be written in polar form as 0.50249 ohm at an angle 84.2894 degree. We have computed armature current Ia equals to 160.375 ampere. Now we shall calculate power factor angle. Phi equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in phasor form as Ia equals to Ia at an angle phi, that is equal to 160.375 ampere at an angle 36.8699 degree. Expression for open circuit EMF per phase, E0 equals to ET minus Ia into Zs. Taking terminal voltage per phase ET as reference, we get E0 equals to 230.9401 at an angle 0 degree minus 160.375 at an angle 36.8699 degree into 0.50249 at an angle 84.2894 degree. That gives us 272.64 minus J 68.961 volts. This may be written in polar form as 281.224 volts at an angle minus 14.1947 degree. A 50 HP 3-phase 440 volts 50 Hz 6-pole star connected synchronous motor has an armature resistance per phase of 0.1 ohm and synchronous reactance per phase of 2.4 ohm. The motor is operating underexcited with a power angle of 20 degree electrical. The generated EMF is 240 volt per phase. We have to calculate armature current, power factor and HP developed. Let us first write down the given data. Line-to-line terminal voltage VL equals to 440 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3. That is equal to 440 divided by root 3. That gives us 254.0341 volts. Generated EMF per phase E0 equals to 240 volts. Power angle delta equals to 20 degree electrical. Generated EMF per phase may be written in phasor form as E0 equals to E0 at an angle minus delta, that is equal to 240 volts at an angle minus 20 degree. Given armature resistance per phase Ra equals to 0.1 ohm, synchronous reactance per phase Xs equals to 2.4 ohm. Let us now write down the synchronous impedance per phase in phasor form. Zs equals to Ra plus Jxs, that is equal to 0.1 plus J 2.4 ohm. This may be written in polar form as 2.4021 ohm at an angle 87.6141 degree. Expression for generated EMF per phase E0 equals to ET minus Ia into Zs. Therefore, expression for armature current in phasor form Ia equals to ET minus E0 divided by Zs. Taking terminal voltage per phase ET as reference, we get Ia equals to 254.0341 at an angle 0 degree minus 240 at an angle minus 20 degree divided by 2.4021 at an angle 87.6141 degree. That gives us 36.1746 ampere at an angle minus 16.7661 degree. Since the motor is under excited, power factor cos phi equals to cos of 16.7661 degree equals to 0.9575 lagging. Let us now determine input power. Pin equals to root 3 times VL into Ia cos phi. Using values we get root 3 into 440 into 36.1746 into 0.9575. That gives us 26,397 watts. Copper loss. P copper equals to 3 times Ia square into Ra. Using values we get 3 into 36.1746 square into 0.1. That gives us 392.58 watts. Now we shall determine gross mechanical power developed. Pm equals to Pin minus P copper. Using values we get 26,397 minus 392.58. That gives us 26,004.42 watts. Since 1 HP metric equals to 735.5 watts, we get Pm equals to 26,004.42 divided by 735.5. That gives us 35.356 HP metric. A 100 HP 3-phase 440 volt 50 Hz 6-pole star connected synchronous motor has an armature impedance per phase 0.09 plus J 2.25 ohm and has rated full load current of 106 ampere. We have to determine generated EMF per phase, torque angle, HP developed when the motor operates at unity power factor, 0.8 lagging power factor and 0.8 leading power factor. Let us first write down the given data. Line to line terminal voltage VL equals to 440 volts. Since the armature winding is star connected, terminal voltage per phase ET equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254.0341 volts. Synchronous impedance per phase in phasor form ZS equals to RA plus JXS, that is equal to 0.09 plus J 2.25 ohm. This may be written in polar form as 2.2518 ohm at an angle 87.7094 degree. Full load armature current IA equals to 106 ampere. Let us now determine copper loss. P copper equals to 3 times IA square into RA. Using values we get 3 into 106 square into 0.09, that gives us 3033.72 watts. First case, when power factor cos phi 1 equals to 1, input power P in 1 equals to root 3 times VL into IA cos phi 1. Using values we get root 3 into 440 into 106 into 1, that gives us 80,782.85 watts. Let us now determine power factor angle. Phi 1 equals to cos inverse 1, that is equal to 0 degree. Armature current may be written in phasor form as IA1 equals to IA at an angle minus phi 1, that is equal to 106 ampere at an angle 0 degree. Expression for generated EMF per phase E01 equals to ET minus IA1 into ZS. Taking terminal voltage per phase ET as reference, we get E01 equals to 254.0341 at an angle 0 degree minus 106 at an angle 0 degree into 2.2518 at an angle 87.7094 degree. That gives us 244.49 minus J 238.5 volts. This may be written in polar form as 341.5547 volts at an angle minus 44.289 degree. Now we shall determine mechanical power developed. PM1 equals to P in 1 minus P copper. Using values we get 80,782.85 minus 3,033.72, that gives us 77,749.13 watts. Since 1 HP metric equals to 735.5 watts, we get PM1 equals to 77,749.13 divided by 735.5, that gives us 105.71 HP metric. Second case, when power factor cos phi 2 equals to 0.8 lagging, input power P in 2 equals to root 3 times VL into IA cos phi 2. Using values we get root 3 into 440 into 106 into 0.8. That gives us 64,626.28 watts. Power factor angle phi 2 equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in phasor form as Ia2 equals to Ia at an angle minus phi 2, that is equal to 106 ampere at an angle minus 36.8699 degree. Expression for generated EMF per phase E02 equals to ET minus Ia2 into ZS. Using values we get 254.0341 at an angle 0 degree minus 106 at an angle minus 36.8699 degree into 2.2518 at an angle 87.7094 degree. That gives us 103.3 minus J 185.08 volts. This may be written in polar form as 211.9539 volts at an angle minus 60.8315 degree. Now we shall calculate mechanical power developed. PM2 equals to P in 2 minus P copper. Using values we get 64,626.28 minus 3,033.72. That gives us 61,592.56 watts. That is equal to 61,592.56 divided by 735.5. That gives us 83.74 HP metric. Third case, when power factor cos phi 3 equals to 0.8 leading. Input power P in 3 equals to root 3 times VL into Ia cos phi 3. Using values we get root 3 into 440 into 106 into 0.8. That gives us 64,626.28 watts. Now we shall determine power factor angle. Phi 3 equals to cos inverse 0.8, that is equal to 36.8699 degree. Armature current may be written in phasor form as Ia3 equals to Ia at an angle phi 3, that is equal to 106 ampere at an angle 36.8699 degree. Expression for generated EMF per phase E03 equals to ET minus Ia3 into ZS. Using values we get 254.0341 at an angle 0 degree minus 106 at an angle 36.8699 degree into 2.2518 at an angle 87.7094 degree. That gives us 389.5 minus J 196.52 volts. This may be written in polar form as 436.2724 volts at an angle minus 26.7733 degree. Now we shall calculate mechanical power developed. PM3 equals to P in 3 minus P copper. Using values we get 64,626.28 minus 3,033.72. That gives us 61,592.56 watts. That is equal to 61,592.56 divided by 735.5. That is equal to 83.74 horsepower metric. Let us now summarize the results obtained under different power factor conditions. First case, when power factor cos phi 1 equals to 1. We have computed input power Pin 1 equals to 80,782.85 watts. Generated EMF per phase E01 equals to 341.5547 volts. Torque angle delta 1 equals to 44.289 degree and mechanical power developed PM1 equals to 105.71 HP metric. Second case, when power factor cos phi 2 equals to 0.8 lagging, we have determined input power Pin2 equals to 64,626.28 watts. Generated EMF per phase E02 equals to 211.9539 volts. Torque angle delta 2 equals to 60.8315 degree and mechanical power developed PM2 equals to 83.74 HP metric. Third case, when power factor cos phi 3 equals to 0.8 leading, we have obtained input power Pin3 equals to 64,626.28 watts. Generated EMF per phase E03 equals to 436.2724 volts. Torque angle delta 3 equals to 26.7733 degree and mechanical power developed PM3 equals to 83.74 HP metric. Now we find that input power Pin2 equals to Pin3 and mechanical power developed PM2 equals to PM3. This indicates that the amount of input power or mechanical power developed does not depend on the nature of power factor. They are equal under both leading and lagging power factor condition, provided the magnitudes of power factors are equal. Whereas under lagging power factor condition, generated EMF per phase E02 is less than the generated EMF per phase E03 under leading power factor condition. This implies that the magnitude of generated EMF per phase does depend on the nature of power factor. When power factor is lagging in nature, generated EMF per phase E02 is less than the terminal voltage per phase ET. This is termed as under excited condition. When power factor is leading in nature, generated EMF per phase E03 is greater than the terminal voltage per phase ET. This is termed as overexcited condition. If armature resistance is neglected, input power Pin is approximately equal to PM, that is equal to 3 times E0ET by XS into sine of delta. If ET and XS are assumed to be constant for same amount of input power, the product of E0 and sine delta is a constant. Since under lagging power factor condition, generated EMF per phase E02 is less than the generated EMF per phase E03. Under leading power factor condition, we have obtained torque angle delta 2 under lagging power factor condition is larger than the torque angle delta 3 under leading power factor condition. So today we have solved a couple of numerical problems on three-phase synchronous motors. By solving these problems, we have learned how to compute the amount of electrical power that gets converted into mechanical power. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.